All right, lesson 41, we're looking at graphs of rational functions, okay? I know we've looked at them before, but this is a little bit more to it, helping us analyze that graph and the function itself and what points on the graph are, okay? And their importance to our function, okay? So to kind of just review a little bit, right? Rational functions are going to look like fractions, right? But they're going to have a polynomial in the numerator and the denominator, okay? So just some review of polynomials first, okay? So if we look at two polynomials, right? First, we have f of x, and we're going to let f of x equal x squared minus 4. And we're going to consider g of x, where that's going to be x squared plus 4. Okay, so if you look at the first one, if you look at f of x, right, when x is 2 or negative 2, then f of x is going to equal 0. So these are zeros of the function, right? They're x values that make the entire function equal 0, okay? However, if we look at g of x, right, x squared plus 4, there are no x values that make g of x 0. Okay? So even more than that, okay, so no x values are going to make this equal 0. Because it's an x squared term, this is always going to be positive because none of them will be 0, okay? And any other real number for x squared will be positive, okay, for any real number. And then if you have a positive number plus 4, g of x, that means, is going to have a value greater than 4 because x squared can't be, well, the function can't equal 0. But for any value for x, then x squared is positive, could be 0. And the function itself has to be greater than or equal to 0 as well. Okay? If we go back up and look at f of x, so x squared minus 4, it can be factored into two linear real factors, right? We could rewrite f of x as x minus 2, x plus 2. Okay, it's just factoring a polynomial. We know how to factor the difference of two squares, okay? But g of x cannot be factored into linear factors because it's the sum of two squares. So we remember that this then, g of x, is called an irreducible quadratic polynomial because you can't factor it into a product of linear factors. Okay, so it's an irreducible quadratic polynomial, g of x. F of x can be factored, so we don't say that for f of x. Okay, then since irreducible quadratic factors can never equal 0, right, that's part of what this means, for any value of x, then vertical asymptotes and x-intercepts of rational functions are not affected by these irreducible quadratic polynomials. Okay, so they can't equal 0. They're not going to affect our rational function at all. If they can equal 0, then they could be a vertical asymptote or a rational, a 0 of the function, depending on where they are. Right, that was part of what we went over, was that if this was in the denominator, these would be asymptotes because they're x values that we can't put into a denominator, but they would be zeros if this was in our numerator, because we can get 0 in a numerator, just not a denominator. Okay? These, however, are going to cause a bend in the graph, but they won't really affect the rough sketch. Okay? So that's one thing to consider when we're graphing. So we're going to look at, let's do the one here. So we're going to graph y equals, actually, we'll do a graph in a minute. So then to add on to that, okay, if a linear real factor is repeated, and in the numerator, or denominator, an even number of times. So say you have x minus 2 squared in the numerator or the denominator. Okay, that's an even number of times, or to the 4th power or the 6th power. So if it's an even number of times, it's going to change your graph. Okay? If it's in the numerator, that's where you get a 0 of your function. Okay? So if it's in the numerator and it's repeated an even number of times, then we have to look and see what happens. So if it's in the numerator, repeated an even number of times, it can equal 0, but can never be negative. Right? X minus 2 to the 4th power could equal 0, but x minus 2 to the 4th power can't be negative, because even if x was negative 2, right, you get a negative number inside, but raised to an even power, you won't get a negative number out for y. Okay? So what that tells us then is that the graph of the rational function won't cross the x-axis at the 0 if it's raised to an even number, an even power. It's going to touch the x-axis at the 0. Okay? In the same way, an even-powered linear factor in the denominator is going to cause an asymptote, just like it has before. But at the vertical asymptote, it's not going to jump over the x-axis, it's just going to go to the other side of the asymptote and start. Okay, so we'll see it in a graph, but if you have an asymptote this way and the graph is going like this, here's your x-axis, okay? When you jump over, it will come back down this way because it can't jump across because the sign won't change because it's raised to an even power. Okay? All right. All right. I guess they don't talk about odd powers here. Okay. So just one thing to add, right? We already know how to find our zeros. We already know how to find our asymptotes. But now if we have them to an even power, at that 0, it can't cross. It's just going to touch the x-axis, and it's going to go on the other side of the asymptote, but not jump across the axis either. Okay. So we are looking then to graph y equals x plus 1 to the second power times x squared plus 1 divided by x minus 3 times x minus 1 squared times x minus 5 squared. Okay, so when you are looking to graph functions, right, you start by looking to see if any of them are irreducible, meaning are any of them to the point where you cannot get it to equal 0. Okay, so for example, x squared plus 1 would be irreducible because we can't factor it, and x squared plus 1 will never equal 0 because this will always be positive, so positive number plus a positive number is always positive. Okay, then we're going to start looking at the zeros. And the zeros are when the numerator equals 0. Okay, so it's already in factored form, so that tells us x plus 1 squared would be 0, and we decided that x squared plus 1 can't ever equal 0 for real values. Okay, so we're going to solve this, take the square root. So we get x plus 1 equals 0, and x equals negative 1 is a 0. But we say it's a repeated 0 because it was in there x plus 1 squared times. Okay? And it's repeated an even number of times, because that's our power. Then that tells us that it's not going to cross the x-axis at negative 1. It's going to touch the x-axis at negative 1. Okay? Then you find your asymptotes. Okay, and that's x values that make your denominator 0. So x minus 3 could equal 0. X minus 1 squared could equal 0. And x minus 5 squared could equal 0. All possible values. And then solve for x. So we're going to add 3 here. X minus 1 is going to equal 0. So x could equal 1. And x minus 5. So we get that x equals 5. Okay? Again, 1 and 5 are repeated. So what that tells us is that it's repeated an even number of times, so we're just going to jump across the asymptote, but not the axis. Okay? So that'll help us in making our sketch, right? These are sketches. They don't have to be exact, right? Some of these numbers, when you start raising them to powers, are going to be large. So it's not that big of a deal, okay? Then we can also consider the ratio of their powers. Okay, so if I look at the power in the numerator, I'm going to get an x to the fourth because this is going to be an x squared times an x squared. So it's going to be an x to the fourth over squared, squared, so that's to the fourth, and then one more is to the fifth. Okay, so the ratio of the dominant terms is an x to the fourth over x to the fifth. Okay, so that kind of helps you with your end behavior. All right, then let's put it together for the graph. Okay, so here is my x and y axis. We know we have a 0 at -1. We have an asymptote at 3, an asymptote at 1. So here's our 0, an asymptote at 3, at 1, and at 5. Okay, then we have to decide what the graph is going to look like here, in between, and out here. Okay, so it's positive, so you have a positive number when x is big, right? To decide if we're going to be down in the negatives or in the positives. Okay, when x is large, so big x values, right? You get a big number over a big number, right? Because 10 to the fourth is large and 10 to the fifth is large. So positive divided by a positive. So our graph is going to be positive. So out here, it's going to go this way. Okay? Again, it's just a sketch, so that's okay. Then, in between 3 and 4, okay? Or in between 3 and 5, sorry. You could even figure out an exact value, right? So what's going to happen, right? At, say, 4. So we get 4 to the fourth divided by 4 to the fifth. Okay, so what happens in there? You can look at your asymptotes too. So you know it's not going to, we started this way. You know because 5 is a repeated root in the denominator that it's going to cross over the asymptote but not the x-axis. So it's going to happen coming this way. Then you don't have a 0, so you know at some point it can't touch the axis. It has to turn around and go back the way it came, okay? Because you know what the zeros are. So you know what's going to touch and cross the x-axis. All right, then you know 3 is also an asymptote, okay? But it's not repeated, so that tells us that it's going to cross the x-axis and the asymptote. So it's going to come up this way. 1, right? So then decide, well, we know it's not going to cross the x-axis because we don't have another 0. And then, so you know it's going to turn and come back down this way because you don't have a 0. Okay? Then you get to your other asymptote. 1 is a repeated because it's to the second power, right? So it's an even number of times. It tells us it crosses the axis, or the asymptote, but not the x-axis. So I'm going to start down here again. This is different though, because I know I have a 0 here. So I'm going to come up eventually to -1, and then -1 is a 0, but it's a repeated power. And it's repeated an even number of times in my numerator. So it tells me I will touch the x-axis and then come back. it might even have more of like a curve like this. But as x gets big, you know, you're getting closer to 0 because you're dividing by a larger number in the denominator, because x to the 5th will be bigger. So you get closer to 0, but you won't ever actually equal 0. And that would be the sketch of your graph of the function that we started with. Okay, again, just a sketch. We don't care really about exact values for x and for the y, so I didn't put it on there because we're just looking at an approximate idea of what it will look like. Okay, so it's adding on to graphing your rational functions. We already knew how to find zeros, already knew how to find asymptotes, but now you're looking at those repeated roots and the repeated factors. Okay, and that's lesson 41.